Hello everyone, thank you very much for inviting me. I hope to give you a good and interesting talk. Siva has warned me off too much maths, so I can assure you that there's only 5%. And
you mentioned it was 34.87%.
Okay, and I also have to tell you that the maths is what you have probably all known for decades, just a little bit of algebraic manipulation and listening to what the words mean. So, dynamic feature fusion trees, an invented name somewhat, but to be better than the previous one I had. And I hope I can convince you that there are some aspects of this which are new, simple and flexible and useful. Now about me, I'm getting to be rather ancient. I've been running my little company, Cambridge Algorithmica Limited, for somewhat over 20 years, which is, I think, quite amazing. And it's been just me since 1993, although there were more of us before that particular recession. So let's go into what we're going to talk about. Pattern matching may be a scary thing, maybe not, but I think it's more pervasive of the world than ever before, with computers and machines controlled by computers. So I'm going to say a little bit about what pattern matching is and give some examples to do with the wine business, or the theoretical mathematician's view of the wine business, how we measure performance, whether we're doing well enough at our pattern matching. And then item 5 is the one little bit of maths, the definition of detection gain. And it's rather interestingly based on a theory which is called naive Bayes, which is not actually naive. It's just simple, and it works far beyond what everyone thinks it ought to work on. And then from sort of 6 onwards, description of what I've been doing over not quite a decade on this particular field in various different application areas, why I'm doing it, and then some information on the very latest things that I've been doing, dynamic feature fusion trees, good ways of handling noisy signals and missing data, and just really of recent interest for me, a bit on how this fits with neural networks and even brain functioning, and what can we learn from the way people think, and what can we do that is different from the way people think. Now, please feel very free to interrupt as we go along if the message isn't getting across, or you think something's not clear or even wrong, and I'll do my best to handle it, and if it's going to come up later in the talk, I'll just say so. Okay. Oh, one final thing. I will be putting the presentation slides on my company website, but unfortunately the company computer died last Wednesday. I got it back up working by Saturday, but the website reinstallation has had to be put off for security reasons. But it'll also be on the BCS website. But I just need to tidy up a few final things to do with acknowledgements and copyright. So it will appear. Right, pattern matching is increasingly pervasive. And what does it mean? Well, it could mean something as simple as deciding whether to put the oil warning light on in your car. There's a signal. Is it above the threshold? Does it measure how much oil there actually is in the car, or just does it measure it being above or below some particular sensor? Newer things, a lot of government surveillance going on. Car number plate recognition. Quite fantastic the way it works, really. It's an interesting question about whether we should have it, but it's quite fantastic. Biometrics. I spent a couple of years on the British Standards Institute committee on this. Are you who you claim to be? And should we be allowed to know? And how quickly can we find out to let you get through customs and airport and passport checking? Automatic speech recognition. I've been working on this off and on since 1976. Still doesn't seem to work any better than a 5-year-old child, but it does work better than it used to. More recently, equipment condition monitoring, and I'll mention a little bit about that. And always of interest, the military target detection and tracking, and quite a lot of the work comes from a long history on that. And although it may not seem obvious, processing of communication signals, modems, receiving radio signals, receiving telephone signals, has a lot of similarities. So increasingly we are there. Here's an example, a fingerprint, the machine's view of the fingerprint, which tends to find bifurcations where the prints split, and maps those and their relationship with each other, how precisely the distance is known, how much do things squidge around. It's all very interesting and useful. The eye. I've got some data here on iris processing. A lot of good work done by John Dorgman, professor at Cambridge University. And you can see he's analysed this picture into 2 concentric rings which are nearly spherical. And he's got 8 tracks going around the iris. And he manages to make determinations which allow for about a 5-degree rotation, but otherwise works incredibly well. But with difficulty to make it work as well as people need to use. Now, there are various different types of pattern matching. The one I work on mainly, and the one that I'm almost solely talking about today, is statistical pattern matching, doing it with numbers, in which accuracy of measurement is a virtue, and handling the numbers correctly is a virtue. It's the one that delivers the best performance. But there's also syntactic pattern matching, where sequences and arrangements matter. Now, we saw that on the fingerprint. There are strange connections in your fingerprints, and their relative position is the key issue, because the bifurcations are all over the place in fingerprints. It's just where yours are and how accurately we measure them. But also language processing, automatic translation, automatic speech recognition, word order matters, the sequence is extremely important, and there are a whole set of complexities, which I'm not going to talk about today, that make that more difficult. And the final one that people usually use is neural pattern matching. We all do it in our brains. We compute, but we don't fully understand how, but we know we actually do it very well. And the questions I have are, how did it evolve in a biological system? How do you evolve and create a pattern matching system that actually works, can see images, can hear sounds, can recognize who's speaking, and so on? Now, some scientists think that doing neural pattern matching is the way to do it. We should copy the brain in the same way that our aeroplanes flap their wings and our motor cars use their legs, but I'm not convinced. But I do think it is important and interesting to see the parallels and to understand them. So those are the types of pattern matching. Remember, I'm talking about the first one. So statistical pattern matching tends to fall into 2 classes, supported by the third issue here. The first one is classification. The output is a decision. Is what you're looking at a cat, a dog, a rabbit, a crocodile, or a fox? Okay, it's a hard decision, and it's one of a very small number, modest number of categories. And the input features can be discrete labels, such as does it have fur or not, but they can also be continuous measurements, the size, the number of toes per foot, the relative size of the mouth, the shape of the mouth compared to the head, and so on. So that's classification, giving you an answer, what is it? One of a small number of classes. But there's also regression, which is a mathematical term, which really means you're producing another number out, and that number can be a continuous variable or several of them. And such examples may be, what is the residual life of the equipment? How long, at what time in the future should I schedule the next maintenance period? And this is an important aspect in condition monitoring and is becoming increasingly important. And in fact, there's an awful lot done by the motor industry and the airline industry in which they are monitoring and recording the life and the condition of every engine, every piece of equipment they produce for the whole of its life, and making these decisions on the way. But both of these are supported by models, scientific models, interpretations of what's going on, and putting parameters on them. What are the numbers that describe how to recognize someone's speech? What are the particular sounds, and what frequency are they at, how intense are they, and so on. So models and parameterization, all very important. Now, I'm going to talk mainly about classification. That's the easiest one, and it's the one that I spend most time on. Regression is perhaps a stage towards it, but is also a standalone useful thing. So a typical pattern matching system, we capture a sample, some features. Imagine a person. You want to know whether a person is who they are. You can look at various things. One of them is their height. You can make an estimate of their weight. These things, you feed this in to something that analyzes the features, and in a learning phase, enrollment, training, or whatever, a model is created and some numbers are put in to describe how you are you, how high you are, how heavy you are, what color your eyes are, what your fingerprints look like, and so on. And this is stored. Some later stage, at the border control, someone wants to confirm you are who you claim to be. You throw the switch down here, capture the same information and feed it in and match it, and you get some number out which you then compare to a threshold to determine whether you are believed in your claim, I am John Smith. Okay, so the whole concept is very easily involved with that. Enrolment, matching. That's really how it all works. Now I've got some examples here. This is some wine data. I'll describe it on the next slide, but what you need to know is that there were 3 classes of wine that are being considered here, and they're represented by 3 different sets, and there are a whole load of measurements on them, and these 2 particular measurements are the amount of ash that is detected in the wine and the alkalinity of the ash that's detected. We'll perhaps consider a little more. And this is a scatter plot of some 30 or 40 vineyards and what their wine is like. And that is being used by me in some of the examples, that sort of data, to learn how to recognise which one of these 3 wine types, which grape variety, the vineyard is using without being told, but just by measuring some chemical composition of the wine itself. And it's a great fun one because the data is difficult but not too difficult. So, the data set. There are 3 classes, 3 grape varieties. I don't know what these 3 types of wine are, I'm afraid, but the total number of samples in the data set, which adds up to 178, is these. And these are the measurements. Really important one, alcohol. We do generally view wines as differentiated by the amount of alcohol. Malic acid, it's the acid in apples, and it features a lot in winemaking. I used to do home country winemaking. The 2 we just looked at, ash and alkalinity, the amount of magnesium, all sorts of other things, the colour intensity and what the colour is. And these are all very useful in analysing the wine and working out what the grape variety is. And I think I can tell you that if you do all that, then you can find out nearly every time what the grape variety is. This is some raw data, very simple arrangement. I just thought I'd show you this to show it's not too frightening. This is the wine data. There are 13 features that are measured, 13 actual measurements, and each line here represents the one vineyard. Okay, so the 178 vineyards have been provided data and test results, and the first column is the true answer, which grape variety is it? And it goes 1, 2, 3. Okay, and these are all 1 at the beginning. Another column over here at the very end, I've split the data personally into 3 buckets, 1 for training, 1 for what's called validation, and 1 for evaluation. So it's 1/3 of each. And the reason for doing that is that you mustn't test your processing and your parameterization on the data where you derive the parameters from, because otherwise you get an over-optimistic view. And there's 3, but I'm not going to describe why we have the validation stage separate from the evaluation stage. We don't have enough time. Here's some more wine. This is the alcohol level. It's the only one I could work out what the scale was, because the numbers are on some measurement scale, and this is clearly percentage alcohol by volume. Proline, not quite sure what that is, some chemical substance, and there does seem to be a fairly strong relationship between the 2. And you can see that the red pluses are easily separated on proline and not quite so easily separated on alcohol, but the proline doesn't contribute much at all to differentiating between 2 of the other grape varieties. But there are other measurements that can help with that. So looking at these sorts of scatter plots gives you a feeling of the task you're giving the computer program doing your pattern matching. We then get on to a very important issue. How do we measure performance? Now, there's no point in building things if you can't tell how good they are. Okay, you can't sell them, you can't claim you've got the best motor car, the fastest, the strongest, the most beautiful, the most comfortable, unless you have some measure of this. So in pattern matching, and there is a problem in pattern matching, which I was first made aware of back, I think, in about 2003, with the great interest in biometrics and talk of the national identity card. And that is that people talk, even well-informed people, purchasing, the community of purchasers talk about the error rate as a single number, but it doesn't actually mean anything. So I want to convince you that there's more to performance in pattern matching, all sorts of pattern matching, than just a 1-number error rate. Now, every pattern matching system that I know of has a big control, and it should be on the front panel, and it should be marked detection threshold or operating point. And it's the position of this that makes the trade-off between the two types of mistakes. Making a false alarm, for example, saying someone is who they claim to be when they're not, or missing someone, declaring that someone is not who they claim to be when actually they are. And by making the system more or less sensitive, you change the ratio, the proportion of those errors. And the operator of a system can set that up to be what is most beneficial for that organization. Are they driven by being crucified for making mistakes and denying people access, for example, to their money, to their country, to their house, or are they concerned to make sure that they don't overload the secondary checks that have to be undertaken when someone is marked as not allowed in when really they should be? So that's one aspect, and it's a very easy knob to change, and it affects the operational cost of using the system. But it's only the implementers, the algorithmic designers, the system implementers, the people who make the decisions between the hardware and how powerful it is and how quickly it's going to operate and how much it's going to cost, that can actually affect the performance. The man who turns the knob on the front doesn't change the performance of the machine. He just determines which bit of the performance he's most interested in. It's like how hard you press the accelerator in the car. Okay, there may be a lot of power there, but if you never call on it because you don't want to, that's fine. So the real thing we're interested in for performance is called the receiver operating characteristic curve, or the ROC curve. And you'll hear me talk about this an awful lot. And it's a very strange word, receiver. And I believe it's all down to the use of the radar systems for detecting aircraft in the years between about 1930 and 1940. That's when the term came in. And it's all to do with radio receivers, but it's called receiver operating characteristic, but it's the measure that allows you to determine the overall trade-off between false alarms and misses. Now, some graphs, a lot of graphs I have here in place of the equations. I'm sure you'll appreciate that. The false non-match rate, also called the miss rate, it depends what you're trying to do, but let's say that you're trying to accept people's claims of identities. That's a very easy one. The miss rate is you miss someone being truthfully who they claim to be. It's a mistake. The false match rate or the false alarm rate is the opposite, that they're an imposter and you accept their claim. And the acceptance threshold, that's the big knob on the front of the machine. As you change the threshold, the number of genuine people accepted drops down and eventually becomes zero. Everyone's refused entry. And the other one, the false alarm rate, goes up. So you've got these two rather complicated graphs, and they cross over at some point, an equal percentage here, which is called the equal error rate. And that is a useful number, but it doesn't tell you by any means the whole story, because the useful operating point probably will be well away from the equal error rate, so it matters what the curve does in other places. But you can actually embody the whole of that data in one curve, the receiver operating characteristic curve, which is very nicely shown here. So this is the false accept rate as a percentage on a logarithmic scale. We do things on a logarithmic scale because that way we can express the whole of the range of performance of a machine that someone might be interested in, between 100% and an infinitely small percentage, which we never quite get to. But anyway, as you change the operating point, turn this big knob on the front of the machine, which is never actually really there, you move where the trade-off is. So this isn't a particularly good device. I think it's hand biometric. Yes. So it's got an equal operating of about 12%, 13%. Okay, so it's not really a very good biometric, but it's very useful for showing the curve. So as you change the knob, you move up here, okay, and you don't want to miss people at 100%. You want to be perhaps somewhere around here with a false accept rate that's tolerable for double checking, but not upsetting too many people. So receiver operating characteristic, one curve that tells you the whole story. It's very useful. Now we get on to the maths.
The question is whether there's a parameter missing, the cost of a mistake. You said it was the whole story, but I think there's another factor.
Yes, there is. If I had another hour, I would talk about mathematical representation of cost-benefit analysis, on which I have worked. The technical story of how well the equipment works is represented in pretty much its entirety for a general pattern matching system in the receiver operating characteristic. How beneficial that is in particular operational circumstances does depend on also adding in the costs of the two types of failure and the trade-off between them. Because obviously, if you let people in when they shouldn't be allowed in, they will use your social security, steal your property or whatever else. But if you turn away your valid employees, customers, citizens, there is a cost to that in how strongly they complain in the appropriate way. But it's not determined. There is nothing you can do in the equipment apart from make the ROC performance better that will actually really affect that. Does that answer your question? Yeah. So it's how you use it as distinct from the operational performance of the equipment.
And the occasional, are you sure?
Yes, maybe. Right. I have this concept in my mind, detection gain, which is a useful thing to use on a pattern matcher, and it's defined, the detection gain is based on evidence E, evidence the feature measurements. And in this maths, I'm assuming that you're trying to detect a target. It could be an imposter in a biometric situation. It could be an enemy aircraft in a military situation. The probability of the target being there is usually very small. But the detection gain that you get is the probability of the target being present when you look at the evidence compared with the probability of the target being present just on the basis of prior knowledge before you've looked at the evidence. So it's what you get out of the machine, the gain the machine gives you in doing the job. And that's a very reasonable definition, and it's a ratio. Now, you can take that and add two other equations, which I haven't given you here. One of them is Bayes' rule, which is the one that's to do with conditional probabilities. The probability of A and B happening is given by the probability of A happening, given that B has already happened, times the probability that B happens. And it's also the converse, the probability of A happening, given that B has already happened, times the probability that B has happened. Okay? And the other one is that probabilities of all the things that might happen sum to 1. So there's this equation and two others which are well known, and if you manipulate them, you get here. And this is an exact equation. The defined detection gain based on the evidence is 1 over the probability of the target being present plus the probability of the target not being present divided by this thing, which is the likelihood ratio target to non-target given the evidence. So this is a measure of the equipment performance, and the probability of not the target and the probability of the target are prior information or prior circumstances to do with how many people are at this time attacking your aircraft carrier or how many people are trying to get into the country or break into your office. Okay, so this is the technical one, and it's exactly equal to that. The probability of getting the evidence from a target divided by the probability of getting the evidence from not a target. And it's called the likelihood ratio, target, and I've added the bit on the end, target to non-target. If the probability of the target being here is very small, then the detection gain given the evidence is approximately equal to, often very close to, the likelihood ratio target to non-target. So that's that's something you can measure precisely on the equipment, and it's very useful because it ties in with the meaning when the probability of targets, the bad thing happening, is very small. We now have what happens when we have a multiplicity of features. The likelihood ratio given the evidence is a function of evidence type 1, evidence type 2, evidence type 3, up as many as you've got. And you can expand this as the probability of evidence type 1, evidence type 2, evidence type 3 given the target. This is a multi-dimensional measure, and the same probability given not the target. If we then make an assumption, big assumption this, that the features are independent, then the probability of these evidences separates out. So we can do P of E1 given T over P of E1 given not T, which is the likelihood ratio of evidence 1, and we can multiply that by the likelihood of evidence 2 and evidence 3. And that is true if all of the evidence measures are independent, if there's no correlations between them, which is not always the case. But it actually turns out that even if it's not true, a lot of the time multiplying these likelihood ratios together gives you a very good way of fusing features in your pattern matching machine. And that's everything I'm talking about is based on that. So we now have some measure from our biometric machine, and we want to turn it into a likelihood ratio. Raw scores coming out of machines. People build a machine and it measures the count of the number of errors sort of in the match of the bifurcations and where they are. And it's a count, it's a number. It's on an arbitrary scale. It works, it's useful, but it's on an arbitrary scale. It will be different from another measure, for example, how well your iris matches, which you might want to combine the two in a really sophisticated biometric using both fingerprints and iris scans. So it's meaningless to combine scores from different arbitrary scales. You've got to put them on the same scale somehow or other. And that's what score normalization does. And you generally find that these arbitrary scales tend to have two main characteristics. There's ones where high scores mean better match, so they're based on probability, something related to probability. And there's ones where low scores match better because they're measuring the distance between two things, and if they're closer together, then they're more alike. And scores related to linear probabilities are usually best combined by multiplication, so that's the likelihood ratio approach. But scores closely related to logarithmic probabilities are usually better combined by addition, which is the log likelihood approach. So what we need, major part of pattern matching machine, can be interpreted as score normalization, and in all my machines it is score normalization. Other people may have a slightly different view. So here's an example back to our wine case. We've got the alcohol versus the malic acid. You've not seen that one before. I've only got two classes this time because we're doing a two-class differentiation most of the time. All problems of classifying things as three classes can be done as problems of comparing two classes and then doing it twice or three times. Okay, so you can see here that the class 2, wine type 2, well, grape type 2, is down here to the southwest of grape type 1. Whereas on a different measure, the ash versus the ash alkalinity, which you've seen before, that they're the other way round. The type 2 is more to the northwest than the southwest. So if you were to look on this scale, you'd see that larger numbers mean that it's more likely to be class 2, and on this one, larger numbers, well, this one, and this one, larger numbers are likely to be class 1, and smaller numbers are likely to be class 2. So we need to resolve that, but we also need to deal with the differences of scale. This scale goes from 0 to 5, this one goes from 0 to 40, this one goes from 9 to 15, the alcohol content, and this one goes from 0 to 5. So they all have different scaling factors as well. So we need to do something to normalize those, and it can get a little more complicated. So this is one of the ones we're looking at, the raw features, the ash versus the alkalinity of the ash. This is after a simple normalization approach, which is computed using the log likelihood ratio. So these numbers all center on 0, and this is minus 100, minus 10,000, plus 100, plus 10,000, and the same here. These are effectively the ratios of how much more likely it is to be one class than the other. And you'll see that they're all divided so that if you drew a line at 45 degrees like that, all of class 2 should be, if it was easily discriminable on this measure, above that line, and all of class 1 would be below the line. So it's actually rotated things, it's scaled them to make it so that is always true. If you drew the 45-degree line, that would be one simple approach of making a decision. Okay. Now, how do we do the parameterization? This is where it gets complicated. If you want me to give up on this, I will. We can move on to other things, but I think we've got time. Okay, I've got some examples here, hand biometric scores. This is a plot of the miss rate for genuine people versus the acceptance rate of imposters. And you obviously want to be somewhere around here, probably. Now, the red lines are the actual plots of the data that was used for training. And believe it or not, this particular set of features is one that's very easy to model mathematically. They're not all that easy, but I've chosen this one to explain it as it is. The green lines are what the mathematical model says. And you can see that they're extremely close, which is nice. And even better, if we plot the probabilities not on a linear scale, but on a log scale, going 100 down to 1%, a tenth of a percent, a hundredth of a percent, a thousandth of a percent, you can see that they are also very close, even when you're down in the tails. So that's really, for that particular set of biometric measurements, the parametric model that I'm using works extremely well and is a good one. Okay, so but they're not all that easy. So it's done by fitting probability density functions, PDFs, the probability of getting a particular score out of all the people who are not imposters and out of all the people who are imposters. Easier to appreciate, sorry, I didn't explain that very well. These are cumulative probabilities. That's a count from minus infinity up to this number, and this is the count from this number up to plus infinity. Rather than looking at the cumulative probability density functions, if you actually look at them, if you plotted a histogram of the data points with the score here, they would fit quite closely to these curves, these non-cumulative probability density functions. Okay, so most of the genuine people would have a low score, and most of the imposters would have a much higher score, and the tails fall off faster for the genuine people than they do for the imposters. So if you apply this normalization, this is the actual data. The red lines are the actual data, so there's obviously a lot of sample points, and the green lines are what the parametric model says. Okay, so we've seen that one before. If you plot the acceptance threshold again against the two error rates, you actually find there's two plots here. There's the original one before normalization, and there's the one after normalization. These two curves sit over the top of each other. They're not changed at all by the normalization. Okay, and that is always the case if the normalization is monotonic. And I'll come back to that later. It's quite important. But so the normalization has not actually done anything bad it's not changed the ROC curve at all. And again, that can be seen on the next slide. So this is the ROC curve, and it says here, set B, which was the original data, transform set B, there is no difference. Every single point on the ROC curve is the same, and that's because it fits the model very well, and it's a monotonic transformation. And this actually is the transformation. This is the original score that came out of the machine built by Michigan State University, and this is the transform score, which it turns the original score into a likelihood ratio. And you'll see it is monotonically increasing. That's very nice. They aren't all, and in some cases with good purpose, but mostly if you don't have a monotonic function, you should be worried.
What does monotonic mean, please?
Monotonic means that it doesn't go up and down, it only goes up. Or if for a different type of curve, it only goes down. Okay, so it doesn't have squiggles in. Okay? Right. So this is the actual transformation. And it's, sorry, the transformation. So if you had a score of 150, the likelihood ratio would be about 0.5. Okay, and it's worth remembering that because we'll come back to that a bit later. Now, on some other data, the transformation was not monotonic. It went down at the beginning and then it went up. And that was not desirable for this particular set of data. The mathematical model for this other score mechanism for facial biometrics was not good, and the mathematical models that I used didn't fit very well. And it wasn't appropriate for it to do this, given the actual data. But you can stop that happening by making an assumption as a bodge, roughly a hack. Okay, and if you do that, it will only affect a very small number of scores, and it will leave things relatively tidy. And so that can be a good thing to do. But a better thing to do would be to find a set of mathematical models that fitted the data better. But sometimes the data is so pathological you can't do that. Now, what do we get out of all this? This is facial recognition using it's facial recognition and hand recognition, two biometrics, face and hand. And the original face data is this red one. The original hand data is this one. These are the ROC curves, so you can see the trade-off. The nearer you are to here, the better the biometric. The nearer you are to here, the worse the biometric. So curves down there are good, curves up here are bad. The suggested method by others who were researching this data was that they would take these two measures and produce a weighted sum of the scores. And that would give them a better biometric. And that's actually what's done here on the blue line, added untransformed data. And you can actually see that although the combination is good here, there's a range of the ROC curve, which has a high false accept rate, but a lower miss rate, where adding these two things together actually makes the machine perform worse than just sticking with the face data alone, which I think you will agree is not a very desirable way to proceed, because you've actually done some processing which has made the performance of your system worse than if you'd only bought half of it.
And why don't you use a tirage system, so you actually look at one and then look at the other, rather than actually combine them? Because surely combining them is a bodge as well, isn't it? As you're saying, you're getting a worse performance.
Are you suggesting that the two individual machines should make a decision and then you should vote? Because if you vote, you're not.
And say you eliminate, if on one machine says, there's obviously a false, then you eliminate it immediately, because it goes out. You use the worst one for doing the elimination. Then the ones you're questionable about, you then throw into the other one. So you actually, you can do a division, can't you, really, and look at the ones which are only in the, could be possibly wrong. The machine could be wrong.
The way you know, in that situation where the two machines vote individually, if there's only two machines, you can't take a majority vote. So if the two give a different answer, you've got a problem. If the two give the same answer, presumably you haven't got a problem. The trouble is that one of the machines is more reliable than the other in some circumstances, and the other one's more reliable in other circumstances. And it's very difficult to do to accept that. But if the machines deliver you a likelihood ratio score, you can actually get them to do that, because the likelihood ratio will incorporate into it. This machine knows it's better when people have big round faces rather than long thin faces, and the other one maybe does something else. So the likelihood ratio can be used by the machines themselves to recognize where they're more reliable, rather than just a vote.
Well, I was thinking that you use the hand one first to actually, get rid of the ones which are obviously false. Then you have a bandwidth where you have some which are contentious. Then you put them onto the face biometrics, because they're better at refining it. Would that be best, or would you do it the other way around?
Okay, there are circumstances. Medical diagnosis testing is a very common one, where the cost of doing the tests is so expensive you want to minimize the number of tests. Right. Okay, what I'm talking about here doesn't take that into account, although it could. Yeah. Okay, because it's assumed you'll be making both tests in every case anyway. Okay, but if you do make both tests in every case, it's better to combine the likelihood scores, multiply the linear likelihoods or add the log likelihoods, than it is to make any consideration before you combine the thoughts of the two machines. It's a bit like error correcting codes in communications. If you use soft error correcting codes, you actually get better communications performance than if you use hard decision codes, which we used to use long ago before we had computers that were quite powerful enough to do the soft decisions. Okay, so we're back here, and I'll come back to this in a little bit, but we've got just adding the unnormalized scores gives you worse performance on part of the operating characteristic, but adding the normalized scores gives you better performance over the whole of the operating curve, which is good news. So, now the question, why am I here doing this? I started off working on radio communications in 1974, and within 2 years I'd moved into a group doing speech recognition, which was very challenging and extremely interesting, and we still need better performance. And the way I see it, by using better algorithms and probably more powerful computers and more training data, is the way we're going to get that better performance. Back in 2003, when I was on the British Standards Institute, there was a clear failure in the whole of the biometrics industry, as far as I could see, towards understanding that they needed to improve their performance, and they could do it with multimodal or multi-biometric, so using multiple biometric devices. And in particular, there was a big issue there as to whether the British National Identity Card should use fingerprints and iris and face matching all together, instead of just opting for one of them, which is what they eventually did before they abandoned the scheme. And part of the reason for abandoning the scheme was that they had no hope of making it work well enough to be cost effective. So that's sort of where I came into being interested in pattern matching theory, as distinct from just being interested in speech recognition, which was really what had happened up to then. But since then, I've seen some commonality with work on demodulation of radio signals. Now, I have to say, in all the work I've ever done, I've made more money out of demodulating radio signals than I've ever made out of automatic speech recognition or biometrics. Because it's something that there's more people buying, and they want it now, and we can do it now. So that's good. But the demodulation of radio signals, I was working on multi-algorithmic demodulation, and in particular using this was for multiple FSK, if any of you are interested, in using coherent demodulation and non-coherent demodulation. Now, the old-fashioned view would be, oh, coherent demodulation is better, but it's more expensive because you need a faster computer. And this is true. But there are actually, with HF radio, conditions, propagating conditions, particularly dawn and dusk, where the ionosphere is changing so fast that the coherent demodulation doesn't work very well, and the non-coherent demodulation works better. But it can change in tens of milliseconds. So you actually want to do both in parallel and combine the results. And I was using exactly the same approaches as I'd suggested for biometrics, and I'm now more generally suggesting. So that was interesting. A lot of the pattern matching approaches don't take a detailed enough view. And I think that's probably the same with everything. When you look at the detail, everything becomes more complicated. But it's only when you actually worked your way through all of that you can make things better. There's another issue coming up. Has anyone bought a 1 terabyte disk for under £100 yet? Right. I have a computer on my desk that is 100 times more powerful and cost me a week's pay, week's graduate salary. It's 100 times more powerful than the machines I first worked on back in 1974, which cost years of graduate salary. And we had one special processor which cost 11 years of my graduate salary. And it could do between 6 and 12 million floating point operations a second, something that now my £500 desktop can do 100 times over. So there's a vast change there. In that I am soon to get, I hope, 250 gigabytes of speech recordings to work on speaker identification. And this is compared to maybe a few megabytes as to what would have been practical only 10 years ago. And the nice thing is I can store this on a disk that cost me less than £100. So I just delivered it to the people who've got all these recordings, and they're going to send it back soon. And the last thing, of course, is very interesting. I think it's very interesting, you may not, but I do. And there are actually quite a lot of benefits that creep in over society, so that's why I'm doing it. But there are problems. Okay? I've already mentioned the one on this slide. If you add the unnormalized scores, even though they're both they're both probability scores, they're both going in the same direction, they're not normalized to be likelihood ratios to have some mathematically sensible meaning. And if you're doing that, you're going to get worse performance. Okay, so that's one of the things I saw. There's another one. This was iris ranking, iris pattern matching. There's a very good iris pattern matching system, which I've already mentioned, produced by Professor John Dorgman, who got the OBE for his work, and it really is very good, and he's a very good scientist. But whole iris code ROC curve is here. I was looking at his data, which he very kindly provided to me, and I wanted to do something on multimodal, and I split his data into two. I'm struggling to remember how it was, but I think it was the inner bit of the iris versus the outer bit of the iris. Subset T1 and subset T2. When you actually look at it, you get better performance by using subset T2 and ignoring subset T1. So, you know, that was interesting that he was using all of the data and combining it in a way that made his performance worse than if he'd thrown half of it away and just used the other half. So, you know, I now worry about that all the time. I spend all my time looking at people's stuff and saying, if we throw half the system away, it might work better.
On the iris pattern matching, is it likely to be because he was measuring the outer eye and the inner iris, and don't your pupils dilate? So therefore, isn't there a variability on that inner one anyway?
There is a variability, but he takes... I'm struggling. I have to say, I cannot honestly remember what the two subsets of the data were, but I think they were the inner and outer bits. As the iris muscle moves in and out, the ring gets compressed, so all the same flesh is still there, but it's just compressed more. It's not that the inner bit disappears.
No, it doesn't disappear. It just changes.
It changes a bit,
diameter.
and it is possible that the outer bit changes less, and that could be the bit that's more reliable. I honestly can't remember, and I'm not even sure I ever knew. Okay, but I think it was, as I say, the inner and outer bits of his. He had 8 concentric rings, and I think I split them into the inner 4, well, to 4 and 4, and they would necessarily have been inner and outer. But he did, in the system he had, the processing very sensibly took into account the opening and closing of the pupil in making sure that the right bits of the iris were still matched, because it was assumed, and I assume he used a linear compression, but it might have been more complicated than that.
You said he had 8 bands.
Yes, 8.
And you said you took 4 bands and got a better result. Did you think of taking 2?
No, I didn't go any further on that because I was trying to produce a paper to give at a conference in Washington. And I had enough.
Do you think, just now, just thinking about it, do you think it would have made a difference?
I don't know. I think if it is the concentric rings issue and the fact that the inner ones change more than the outer ones, then maybe 3 or 5 would be better than 4. Whether it goes down to 2, I don't know. But it does mean, I mean, you're very right to be asking these physical questions. What are you actually measuring, and what are the real-world difficulties and constraints? Because this is actually very important, and you need, I fully accept, you need to be very careful in all of this wonderful mathematical processing in forgetting what effect the real world has, which you could probably work out just by using a bit of common sense. But yeah, you're right. I do this all the time in speech. I spend all my time in speech processing, listening to signals and looking at pictures of them, rather than just saying, oh, it's a speech signal and I don't need to know anything about it, you know, apart from its mathematical properties. Okay? Yes, I think we need to progress on a bit faster. Right. I will ignore the stuff in light grey because that is just philosophy. Right. Dynamic feature fusion trees is a step forward from using two features and combining them together by normalization and adding the log likelihoods. Okay. Pairwise fusion, I haven't given you all of the detail, but it is pairwise fusion of normalized features is close to the best thing if the only things you've got are those two measurements. And it is almost certainly true that it's very good if they both have bell-shaped curves, although they are not required to be Gaussian. But if they have one peak and they both go down, that's good news, and the pairwise fusion works very well for that. So I have this case. If you add an extra feature, you had two features and the third one creeps in at greater expense. The first thing you could do is what you were always doing with the two features and then treat the third one as an addition. And you should obviously do that because what you were doing with the two features was good, and adding the third one, well, that might be doing it the same way might be good enough. If it isn't better, you should be a little bit worried, and then perhaps you should start looking at three ways. But seeing that it's better adding it, so you've added two by normalization and fusion, and your third one comes along, you take the result of the two and add the next one in by normalization and fusion. And you also do a bit better by seeing if you did it in a different order, so feature 1 and feature 3, or feature 2 and feature 3, and add in the third one last, just to see if that goes better. And if one of those works better, that's great. But it seems to me those are obvious things to do because you already were making the best use you could out of two of the features, the ones that you got most cheaply, say. And then the third one you could afford a little bit more for a higher performance sort of upmarket system. Why not try patching it on separately and see how well that works, then try integrating it, and then try something more complicated, perhaps like principal components analysis, I don't know. But anyway, that's why I started off on dynamic fusion trees. And here is a picture of the concept. There's a lot of things to discuss here. Right. Two raw features, we normalize them and fuse them by addition. And then we renormalize, because if these two features are correlated, then having fused them together, you won't have something that adds up to 1. Because there's some redundant information here which means that you've got an unnormalized probability density function you need to renormalize. So you do that with two raw features. You can take a raw feature and some noise. I'll come to that in a few minutes. And you can produce the normalized feature taking into account the noise, because you've got a mathematical model of how this noise affects the raw feature. You'll generally find that what happens is that the probability density function is broadened, and it gets broader and broader and broader the more noise you add in. But exactly how that happens can be modeled by a lot of training data.
Surely you either know that it's noise or you don't know that it's noise. So if you know that it's noise, why do you bother with it? And if you don't know that it's noise, why don't you think it's just another raw feature?
Right. What I'm saying is you've got a feature that is affected by noise, but you've got an independent measurement of how bad that noise is. It might be a low-level noise, in which case this feature is still useful. And it'll be more useful if you know how much noise is added in with it.
Oh, so what you're trying to do really is to almost subtract the noise from the raw signal.
Well, yes, you can do it by subtraction, but people do. But there's a second stage of processing where you can't subtract it, but you can say you know how much damage it's causing.
Yeah, okay. So subtract may be too simplistic, but neutralise.
Neutralise, yes.
Yeah,
well, acknowledge the damage it's doing.
Yeah, okay.
Okay. You can have it so that one normalized feature feeds forward to two different things because it's correlated with them. Okay, and the noise may be only relevant after you've already normalized something else. Okay, and finally, after any number of levels, you end up with the thing you're going to threshold to make your decision. In the case of a biometric, is he an imposter or not? Okay, so this is the whole concept of dynamic fusion trees. But the really important thing is, which order do you connect the raw features in? And how do you build the tree? How do you decide what a good tree is? Now, it's very interesting. There is a pattern matching technique called decision trees, which work on the basis of if you can find any feature that is reliable over part of its range to give you the classification, use that. and don't ignore all the other features if the measurements fall into that particular category. And only use the other features if it's outside. So where it's certain, you use it straight away. Now my philosophy is different. I might explain a bit more of this later. But roughly, we know from the mathematics that I showed you that if the features are independent, then adding them together is the perfect thing to do, and you won't have to renormalize. It's only if they're dependent that the renormalization is necessary. So what you should actually do is to fuse the things that are most correlated first, because they can help each other, and if you did the fusion later, you would find that the correlation had become obscured, but it would actually damage the quality of your results. So by fusing things when they are known to be correlated, you are minimizing the damage caused between the perfect world, uncorrelated features, and what you've actually got before you. So my view, and what I'm working on at the moment, is that you normalize the features, you look at the correlations between all of them, and you choose the pair that are most correlated, and you fuse those and generate a third feature, and maybe throw the two original ones away. But that's another question which I'm not going to go into. So you've now got one less feature, and you then do the same. You look at all of the correlations, choose the two that are most correlated, which might include the fused one, might not, fuse those, and you keep on doing that until you've got one left. And then you make your decision on that one. Okay, so that is the general approach, and it's ad hoc. It's not optimal. I might come back to that in a bit. Right, I'm going to have to skip over these next two slides very quickly. Dealing with noise and missing data. There are some very good techniques. I call them classical methods. They're good because they've been around so long, and they're good because they work. Okay, but they have problems if you haven't got all your feature measurements, or you've got noisy ones. Using a noisy feature might make things worse than just ignoring it, if you don't do the right thing with the noise. If you're using something like principal components analysis, which is an orthogonal transformation, possibly trying to reduce the number of features, but certainly make it clearer what the class distinctions are, and a feature is missing, the whole of your principal components analysis is now wrong. Okay, it no longer applies because you've lost one feature. What people often do in that is they invent the feature value that they haven't managed to measure because it was lost on the way, it was corrupted by noise, the equipment failed or whatever. They invent a value which they hope is realistic by looking at all the other features. But if you actually think about it, how can you add back lost knowledge which you don't know? Wouldn't it be better to have a different principal components analysis which ignore that feature, which is what I come on to here. Now, why not normalize PDFs with no noise levels? That's the suggestion I've made on the previous slide. It does happen at the moment. I'm unkind to claim credit for this. It's been around for years in speech recognition, called parallel model combination, but it needs to be done more rigorously, and it needs to be done more extensively. And we now have the computing power to do it better. When it first came in the late 1980s, early 1990s, we didn't have the computing power to do it well enough. My suggestion, why not just ignore the missing features? Okay, you've got this wonderful tree. If you take out this one, just feed this one straight through. Okay? If this one's expecting this sort of data with this probability density function, have a computation which does this one if that's missing. Or it does that one. Sorry, does this one if that's missing. And you've just got a couple of algorithms here. Because they're only involving two features, it's relatively easy to do. You're not losing everything in the same way as you are with principal components analysis, which may be doing a simultaneous analysis of tens, if not more, features. So why not parameterize your normalizations, assuming a modest number of missing features? Any combination of two features can be missing, and you compute a new dynamic feature fusion tree for the number of cases that you have with two features missing. But I can't say any more on that at the moment. Right, parallels with neural networks. They were very popular, especially in the 1980s, I remember, and they are still good. They still are useful. But the basis that they're working on how the human mind works is an interesting one. And they have not had the success one might hope. They certainly they've not provided that leap to human cognitive ability in our machines. There are similarities between decision feature fusion trees and artificial neural networks. They're both feed-forward networks. They start with lots of features and they combine them and do processing, and you get less and less at each level in an artificial neural network, the same in my DFFT. They apply usually a monotonic nonlinear transformation. It's a sigmoid in the case of artificial neural networks. I've got a bit more on that. And they apply a threshold to the outputs, or they might apply a threshold to the outputs, or do the equivalent, which is the next stage, applies some sort of threshold as part of its normalization. So here are some sigmoid functions. This is the logistic curve. This is the error function, the integral of a Gaussian from minus infinity up to the point here. There's a whole load of other ones, various sigmoid functions, and they're all referenced. These come from Wikipedia, and it majors on the fact they're using artificial neural networks. But the difference is artificial neural networks mainly use an empirically determined sigmoid function. The designer chooses it, and he thinks, oh, it's okay, it doesn't matter much. They might have some parameters. There's often an offset in each node of an artificial neural network, and there may be a width factor, but the general shape of the function is usually not changed. Dispute? Anyone wish to dispute that? Okay, it could be, but it isn't. DFFTs use not a sigmoid, but a data-driven transformation that's the ratio of two probability density functions. There is a theoretical reason for using it, and it is different for every feature that you are going to fuse. And good cause. And the theoretical basis is just Bayes' rule and some other minor aspects. So I have an interesting question. I think that using this explicit normalization approach is good. It's an interesting question, and I think there's a lot to be said for asking this. How did brains evolve? What is there that can evolve slowly in the way that Darwin has taught us in a brain that will gradually allow it to grow bigger and do more and more things? I would love to know. How does it, if it does, as I suspect, derive transforms which are different for every node in neuron in the brain, how does it do it? Why does it work well to ignore the correlation to the features? And there's a whole load of theoretical papers on what's called naive Bayes. And they call it naive because people don't like it. They don't like it works well. It's interesting. Certainly, if you do what I'm suggesting, you don't really have the curse of dimensionality because you don't have to consider every combination of all the features all of the time. You only have to choose the two to join together at the moment. But I'll tell you, consider two features that are identical. By mistake, you've put the same processing node into your equipment twice, and it searches out and finds that they're very highly correlated, in fact, perfectly correlated. So it chooses to fuse them together first. But because they're giving you exactly the same information, there's no new discriminative information in there at all. But the probability density function after you fuse but before you've normalized is the square of the original probability density function. So the normalization you would apply would just be to take the square root. Okay? And then you would be perfectly where you were before. There would be no loss by this fusion of two identical features. So if it's good to fuse two things that are identical, perfect correlation, why should it not also be good to fuse things first which are partially correlated? I know it's not an optimal mathematical argument, but it seems to me to make some sort of sense. There's also the fact the monotonic feature transformation doesn't change the ROC curve, so it doesn't affect the performance, but it does render an unnormalized score normalized so it can be fused with some cause without expecting that the things are measured on different scales. Finally, for discussion later, is what I've described dynamic? Is it new? Is it simple? And is it flexible? Because I've put all those things in the title to please you and drag you in. There are a lot of aspects of DFFTs that draw on previous work. Not all my invention. It's, how long is it now? It's not quite 40 years of work experience. Much of it in this field or related fields. Okay, so I can't claim a lot new, but there does seem to me to be some aspects of it that are very attractive in their simplicity and the cases that I've made for fusing things which are most correlated first rather than fusing things which are least correlated first, or using first, which is really what decision trees do. There is a key issue on selecting PDFs. How do you choose whether to use a PDF that has two parameters, like a Gaussian, or a Ricean, or a Rayleigh function, or a gamma function? How do you choose whether to use something that has more, like a Gaussian mixture, or a Gaussian raised to a power, which is a way of handling kurtosis, in other words, either long tails or short tails in the distribution? There's something called the Bayesian Information Criterion, BIC, and there's other things that are of a similar nature that effectively give you a sort of argument based on information theory as to how much better your performance should be for adding one extra parameter. So if you want to compare a two-parameter function versus a four-parameter function and not be overtraining, making too tight a model of your training data which doesn't generalize to data you haven't seen, then there are some methods of doing that, and that's important to take into account. And as I said, there's this massive increase in computing power, and particularly the storage. I just can't get over. I can get 1/4 of a gigabyte data on less than 100 quid disk. Future work. I've been trying to do it for years, but I'm now actually writing, and nearly had running for today, a GUI-based software package for doing all of this processing. But unfortunately, the lack of diligence on my part, too many bugs, and the computer failing on Wednesday scuppered that. I'm working my way through the database of example pattern matching data from the University of California at Irvine. They have this lovely online database. It's free. The only thing they ask you to do is reference them. Okay, and they've got hundreds and hundreds of real-life data, cancer diagnosis, the wine one that I've shown, which is really a toy, but it's nice because it has characteristics which make it easy to analyze. I'm working on using arbitrary numbers of pattern classes, comparing, if you've got three things and you compare two, and you find that each one is better than one and worse than one, you've got a problem. So I'm trying to find a way of solving that in a way that's meaningful. And also, because I want to do it for automatic speech recognition, I want to find a way of combining this theory with syntactic approaches in which sequence is important, hidden Markov models are important, dynamic time warping is important. You can't take speech and chop and change it and then play it back and have people still understand what it means.
About dimensions, you're talking about sequence, but isn't that just the dimension of time that you can add to all the other dimensions? And then with that is the fact that you can do cluster analysis if you have lots of dimensions. Do you do cluster analysis?
I don't think time is just, it's more complicated than that. There was a very interesting thing I saw recently, that people had taken a paragraph of words. For every word, they kept the first and the last letter and randomly jumbled the ones in the middle. And you could still read it and understand what it was almost instantly. You can't do that with speech. Okay? There's something about the tracking of it. There's something about the knowledge of what's going on in people's mouths, perhaps, that makes you think that it probably matters what the sequence of tongue movements are in terms of the sounds that come out. And if you know that the sequence of tongue movements was impossible, you won't consider that could be something that was said. You'd consider it as noise. So I'm not sure I agree with that one.
That you've left out a huge number of areas that you could be exploring, like finance, DNA, and the military. Have you been tempted into those areas?
I do a certain amount of work for the military, but it's mainly on radio communications. Finance I've avoided because I think it seems to be a very popular field. I think a lot of people made a lot of money out of it. I don't understand it. I don't understand why the average time an equity is held in the world is 22 seconds. Okay, this is beyond my comprehension. I would not be able to contribute usefully to the field.
But it's other people's algorithms doing that.
Well, it is. And they're all passing the money round and round in circles, and we're paying for it. And I'm not quite convinced that it makes money, but it, I'm certainly market trading and does make money, but I mean, it makes money for the whole world. So it is a useful thing, but I'm not sure when it's happening on a 22-second cycle.
Sticking with the biometric analogy, if you're designing your fusion tree algorithm to intentionally exclude data from the set because it's damaged or because it isn't deemed usable, doesn't that potentially introduce a weakness into the wider system, because a malicious user would know that by corrupting a certain set of data they would have to have one less hurdle to jump through? And similarly with the iris analogy, if you would have 8 rings of the iris and you're reducing it to 4 rings, doesn't that in turn reduce the probabilistic success rate of the algorithm, because you're only using half as much data?
There are all good points there that I haven't addressed at all, and there just isn't. It's effectively you're talking about denial of service attacks. Okay, and I mean there's a very good one. If you want to rob a man who is extremely rich and has a house with burglar alarms on, you set them off every day for a week, and then you burgle him. Okay, because he'll have switched them all off because he's so fed up. And that is really what you're saying, and I cannot argue against that. And it's certainly true that if you were to only use 4 iris rings rather than 8, that in the circumstances of someone attempting an attack which exploited that fact, you would be in a greater position of weakness. And it's probably better to try using all of the rings more sensibly and to detect the sorts of attacks that can be made. Now, there's a whole thing in biometrics called, most of the biometric assessment is done in what's called a zero-effort attack. Okay, you assume that people are just going to walk in off the street and pretend to be someone else, but they're not. I mean, one of the most interesting things, of course, is that if you've got access to the biometrics of someone, and you happen to be in a criminal organisation which has 1,000 employees, if you want to send someone to break in through an iris detector, you choose the one of the 1,000 whose iris is closest, and then you try and degrade the operation of the system or degrade the mismatch of his eye. So all of these things are much more complicated, and I accept that, and it's a difficult question in which pragmatics comes into it more than mathematical theory.
Is there actually some sort of heuristic, if you like, for when you're designing your fusion tree algorithm as to how much data is acceptable to exclude before it falls over?
I don't know. The only thoughts I've had on the issue, because I do some work on information security, which is really rather separate, is that if you identify the methods of attack that are in common usage, then if you build a detector for those, you will know, or you will have more knowledge of when an attack is being made, so maybe you would then turn up the acceptance threshold on the other matches because something's not quite right. But more than that, I'm afraid I haven't thought.
You made 2 interesting partial queries. One was about the difference between speech recognition and reading recognition, and the other one was about the evolution of the brain. I'd like to address them both.
Okay.
Speech recognition occurs in a very specific part of the brain, dedicated to that task alone. Reading recognition doesn't. It's much more generalized. In fact, it's much more the center for it, as demonstrated by fMRI, is much more variable between different people who've learnt to read from different standpoints. And it's different, for example, in first and a second language, whereas speech isn't. And that suggests to me that the evolution of the brain wasn't. It isn't the brain. It's a cluster of independent organs that evolved over different timescales, some of the earliest ones for very specific narrow purposes. So we may in fact be dealing with how did the brains in plural evolve, and then it's a question of which one you're talking about and what it specifically is tailored for.
I don't think I disagree with any of what you've said. It all seems to be quite plausible, and it's certainly probably the case that hearing starts before reading, although not before vision. I'm having two daughters who were born in the Netherlands, one of whom went to school at the age of 4 and within a term was speaking Dutch. I'm not quite sure, and I've noticed she's a very good linguist. She speaks German and picked up Swedish within months as well. We are all of the view that she has a brain set that is different from mine, because I'm a poor linguist, because she was exposed at an early age to 2 languages for a substantial amount of the time.
I think you're right, and it's very early. There's a very, very notable paper, I can't remember the authors, but from Berkeley, on that very thing, and they came to the conclusion that a newborn infant of any nationality in any context can recognize and vocalize practically every sound that's feasible to be made, but within about 3 months maximum, the set has filtered down in terms of its recognition and capacity to create those sounds according to the language of its environment. So if you're brought up with 2 languages, your vocalization and recognition set will be by definition larger.
Larger, yes. Right. I think we agree.
But it happens within the first 2 or 3 months from birth.
That I'm not so sure about, because my experience is years. But maybe she's not as good a linguist as she would be if she'd been exposed from a much earlier age.
The trouble is, we've been working on von Neumann machines, and they're very primitive, like the amoeba. And now you see GPUs like Teslas and things like that, which are going to make the quantum leap. Because at the moment, most of your algorithms, you're looking at one specific thing and trying to use it. I've looked at voice recognition since the 1980s, and it's still, not going along, image recognition. But I've got a Tesla now, and you talk about the power of that in my machine, my little PC. I've just got this little box. That really wumps it up, and that's what you want to look at, because I think you will find that sort of dynamic. Mind you, it's still not powerful enough. So
certainly
Darwinism is probably where visual, like most animals have to do, they have to have image recognition first, and then speech comes later.
Yes, I wouldn't disagree with that.
In that iris data, you effectively split it into 2 pieces of sets, and one was more effective, and in fact adding the other one made it worse.
Adding the other one the way it was added made it worse.
So it's almost, it sounds like noise at one level, and you've identified what is effectively a noise set, but your problem then becomes, isn't the classic case where the marketing director says, I know half my marketing budget doesn't work. The problem is I don't know which half.
Yes.
So is that effective? But is it noise, or am I misunderstanding it?
I did have I haven't included it in this presentation, but I did have another slide where is one of the ones to do with merging face and hand biometrics, where one of the biometrics on one of its dimensions obviously had a trimodal feature. It had 3 bumps in it, and for the genuine people. And looking at that, I was thinking they built it very badly, because it almost certainly had 3 separate analysis components, which they then fused into one measure, but the fusion was not done very well. And that's the concern I have, is that if people merge their different sensors or different algorithms analysis, and they do it with indifference to all the stuff I've been talking about, they can actually lose discrimination that they would have had if they'd done it better. Now, I'm not saying they're not doing well, but they could have done better on the data they already had. And I think that's the issue. But, trying to reanalyze the innards of everyone else's machine is not that easy. I just did it on the iris data because it was in the public domain, and because the Professor John Dorgman and I were both going to the same meeting, and I didn't have any biometric data of my own, and he very kindly let me look at his to see whether anything I was doing was sensible. And there were some other arguments that he used actually which have some validity, which is where his stuff wasn't doing as well as mine, it didn't matter because you'd never set the operating point there, because the way everyone is using iris biometrics is that they want a very low false alarm rate. And that was a valid argument. No, I still think my approach didn't make it any worse at that bit of the operating curve. It just made it better somewhere else. And I think I'd rather have made it better than said it didn't matter.
Your observation on losing some data improves the model, or including data could improve a model, we found that significantly changed. Knowing what to lose and what not to lose, we're doing analysis of recognizing when people write in whether they were complaining or what department and who the letter should go to. For years, we had removed words like of and as being completely irrelevant. But actually, the way you write to somebody changes very dramatically if you want something or if you're complaining. So that the use of English and nice words disappear if you're complaining. You will use things like "you will do this," whereas if you want something and you're after something, you'll use much better set of English. And actually, these small words made a massive
difference in the stylistic analysis or the emotional analysis of the written language.
That's it.
Yeah.
And the recognition rate and the success rate was much better.
Once you took into account.
Once we realised that we were excluding erroneously very good data.
So it was the comparison of the word set, someone's dictionary or cohort of the dictionary they were using, was not adequate alone. It was the stylistic aspect which conveyed some emotion or overall intent.
That's it. They would use words which seems unusual, but they'd say things like, "I wouldn't dream of complaining about this company." We'll pick up complaining and say, well, that goes off to the complaints department. But of course, they're doing quite the opposite.
Subtle. Yes.
And but actually, the smaller words, which you could argue to throw away, were the telltales of the mood somebody's in when they're writing it, which often indicates the department they should be routed to.
I can see that. Yes. Similar things happen in speech. The bits you think don't matter in terms of the information content actually do matter quite a bit. Yes,
Thank you.
right.
Thank you, Nigel.
Oh, thank you very much.